So here's where we're at. So now we're going to get into the real heart and soul of physics. So when you look at motion, and basically this is going to be true of all the motion you're going to have between now and after the second 9 weeks when we get into circular motion. You're only going to have two possibilities. You're either going to have constant velocity, in which case you can use distance equals velocity times time. So listen to me very carefully. This is a great equation, but it is a one-trick pony. Okay? It's a great equation. It's amazing. You can use it at the speed of light, any number of things. Okay? But you can only use it if something is moving at a constant velocity. If you see something speeding up, slowing down, you can't use it. Okay? Now, the other option is that you have accelerated motion. And accelerated motion, that's a two-trick pony. What are the two tricks on accelerated motion? What's the two things I can make something do? Connor S.
Speed up or slow down.
Speed up or slow down. That's it. Okay? Every acceleration problem that I write, that's the decision that I have to make. Do I want Connor to speed up? Do I want Connor to slow down? That's it. Only two tricks in town. That's it. Nothing else. That's it. Now, here's the main thing that I want you to see. If something is going to speed up, we're going to look at two things. We're going to look at the sign of acceleration, and we're going to look at the sign of velocity. So the whole point of that endeavor with the dude in the Phet simulation was that you begin to see some patterns. So here's a velocity time graph, okay? And let's say you have a horizontal line. So if you have a horizontal line on a velocity time graph, start with this idea. What does the slope of a velocity time graph give you? What physical quantity is represented by the slope of a velocity time graph? Acceleration, how do you know? Who said it? How do you know? You're right, but how do you know?
Because I honestly don't know. My brain's fried right now. Sorry.
Can I give you a hint?
Yeah.
What units is velocity measured in?
Meters per second.
What unit is time measured in?
Second.
So if you were to find the slope, that's meters per second, which works out to be
Meters per second squared.
meters per second squared. So the slope, there are certain things you have to know without fail. One is without hesitation, the slope of a velocity time graph gives you acceleration. That's it, boom, no exceptions. So what's the slope of a horizontal line? What's that numeric value? 0. So if you have a horizontal line on a velocity time graph, you're moving, but you're not accelerating. Okay? This is you driving down 119th Street at 45 miles per hour. Cruise control on, boom, there you go. Okay? Not speeding up, not slowing down, constant velocity. Now, if you're going to accelerate, you have one of two options. This line can either slope up, or this line can slope down. Those are the two things. So if you're accelerating, either that line is going to slope up or that line is going to slope down. That's it. Nothing in between. Okay? Sydney, you're in a math class. You have a line that slopes up like this. Is that a positive slope or a negative slope?
Positive.
Positive. So we just said the slope represents acceleration. So if it's a positive sloping line, that means you have positive. I have positive acceleration. Guess what? I also have positive velocity. So there's a couple of ways you can determine if something is speeding up or slowing down. I'll show you two methods. Pick the one that fits in your mindset. I care not which one you choose. Some people like signs. It's like, ooh, it's a sign. Okay? So if your signs are the same, both positive, both negative, that means you're going to speed up. So if you see something speeding up, a rocket, an electron, a proton, a squirrel, whatever it is, if you see something speeding up you know that the velocity and the acceleration have to have the same sign. Notice I did not say they both have to be positive. I did not say they both had to be negative. They just have to have the same sign. Okay? So, if something's going to speed up, your acceleration and your velocity just have to have the same sign. That's it. Okay? Not specific to positive or negative. They just have to have the same sign. Now, some people like a visual approach, so here's option number 2. But wait, for additional shipping and handling, I'll show you the second approach. Some people like a visual approach. So here's 0 meters per second. So if this line is moving away from 0 meters per second, you're going to speed up. If this line is approaching 0 meters per second, you're going to slow down. Okay? That's it. That's it. So if you like a visual approach, look at the graph. Oh, right. I'm going away from 0 meters per second. I'm speeding up. My line is approaching 0 meters per second. I'm slowing down. Now, once you hit 0 meters per second, can you go any slower?
No.
No, even freshmen, I've seen them try. Freshmen can't even go slower than 0 meters per second. That's it. It's bottom of the barrel. You cannot go any slower. Now, Sydney, you're back in a math class. This line is coming down here like this. What's the sign of that slope? Positive or negative?
Negative.
Oh, now I have negative acceleration, but I still have positive velocity. Now what am I going to do?
Slow down.
Slow down.
Now I'm going to slow down. So if I'm slowing down, acceleration and velocity have to have opposite signs. Now here's the pattern that you're going to try and find. Oh, negative acceleration means that I slow down. And it can happen. But I can also speed up with negative acceleration. Because if I take this line and I bring it all the way through like this, now, if you remember, yesterday we said there's 3 criteria that you have to meet to change direction. They have to be in a very specific order. 3 criteria that you have to meet to change direction. What are those 3 criteria?
Slow down.
Slow down.
Stop.
Stop.
Speed up.
Speed back up. Is that what's happening here?
Yeah,
Why, Mr. Hanna?
you're slowing down and approaching 0, and you stop, and once you get away from it, you speed back up.
Beautiful. Okay? Now, so the negative acceleration here made me slow down because I had positive velocity. So here's the first criteria. Hey, I'm slowing down. I'm approaching 0 meters per second. I cross 0. Now, do I still have negative acceleration?
Yes.
Still have negative acceleration. I still have negative acceleration. But now what am I doing?
Speeding up.
Because now I have negative
Velocity.
velocity. Cool, right? So now I have negative velocity, negative acceleration, and I speed up. Now, a lot of times what I'm going to ask you to do is put arrows on the graph to indicate if something's speeding up or slowing down. So what you can do is come in here and go, okay, hey, in this region here, I'm slowing down. Okay, so I'm going to put a down arrow on this region until I cross 0. But once I cross 0, then what am I going to start to do? Then I'm going to start to speed up. Okay? So, slowing down, I cross 0, speed up. Now that's what that's going to look like on a velocity time graph. Speaking of velocity time graphs. So this question on the back, when you get to, where's it at? That question on number kind of 22, you're moving at 4 meters per second. So here's the story. So here's the velocity time graph. And that's 4 meters per second for 2 seconds. Now, up to this point in time, when you've calculated area, what units has area always been measured in?
Something squared.
Something squared. Meters squared, inches squared, squirrel squared, something. Okay? It's always been something squared. because it's always been meters by meters, inches by inches, yards by yards, okay? Now you have to take the leap of faith and go, oh man, I've got dimensions that aren't in length, but I've got a rectangle. I've got a rectangle that's 4 meters per second tall and 2 seconds wide. And you're going, oh, Burkamp, that's so weird. Still dimensions. Here's an area. It looks like a rectangle, okay? And the height of the rectangle is 4 meters per second and the base is 2 seconds. I'm just using velocity and time to determine the dimensions of that rectangle. Now, when I do this, I take 4 meters per second times 2 seconds. The seconds cancel out. I get 8 meters. Okay? So, if you try and use distance equals velocity times time, if you think about it, this is like the area of a rectangle. This is saying the area of a rectangle is length times width. But on a velocity time graph, your length and width are your velocity and your time. But again, this only works when you have constant velocity, which is a horizontal line, which just makes this look like a rectangle. Okay. True or false? You can change direction with constant velocity. Andrew.
True.
Really?
Yes.
Really?
If we're in three-dimensional space.
What's the rule? Only in one dimension.
Then no.
No. Because by definition, what do you have to do to change direction? Slow down, stop, speed back up. You can't do that with constant velocity. Now, if you have a straight sloping line on a velocity time graph, which is what you're typically going to have, this is a very specific type of acceleration, what we call uniform acceleration. Okay? So unless you're specifically told differently, you can assume that you have uniform acceleration. Okay? Uniform acceleration just means that the velocity time graph is a straight sloping line, which means your velocity is changing the same amount per unit of time. Okay? That's all that means. True or false? You can change direction with uniform acceleration. Tyler, you shake your head yes. Why?
Because if you have, like, let's say positive velocity and negative acceleration, then you will slow down, stop, and then turn around.
Yeah.
Accelerate.
And that's beautiful. There's a spot-on explanation. And that's exactly what's happening here. I am changing direction with uniform acceleration. The velocity is slowing down at a certain rate, and then it's going to speed up at a certain rate. Cool. Now, let's talk position time graphs. What does the slope of a position time graph give you? Velocity. You're not sure, wow, that position is in meters, that's in time, that slope is going to be in meters per second. Cool, right? Slope is going to be velocity. So, what does a horizontal line on a position time graph indicate?
Constant velocity.
Of what?
Zero.
Zero. Why?
Because your position's not changing.
My position isn't changing. Okay? If you have a horizontal line on a position time graph, what's the object doing?
Nothing.
It's not moving. Time's going by, but guess what? You're not moving. So if you have a horizontal line on a position time graph, that just means that you're at rest. Okay? Because the slope represents velocity, and a horizontal line has a slope of 0, that means that you're at rest. Now, let's say that's at 4 meters and this is 2 seconds. Could I find the area underneath that graph?
Yeah.
Yes. What would it represent?
Velocity.
Nope.
Okay.
What units would you get?
Meter seconds.
I would get 8 meter seconds. Now, in your brief yet brilliant physics careers, what is measured in meter seconds? No, it's a trick question. Nothing. Okay? Nothing is measured in meter seconds. Finding the area underneath a position time graph is like talking to a freshman. It has no meaning. Okay? You can do it, but it's not going to mean anything. Okay? Because the only thing you're going to get is meter seconds. Okay? It's got nothing. Big deal. Meter seconds. Okay? Now, on a position time graph, Miss Delzer,
Yes.
is that showing an object speeding up or slowing down?
Speeding up.
How do you know?
Because the slope is starting off shallow and then it gets steeper.
Starting off as a freshman who was shallow, you're turning into an upperclassman and you're getting steeper. Okay? Speeding up. Cool. So by default, Mac, what would this mean? What would the upper line mean? Speeding up or slowing down?
Slowing down.
Slowing down. Because if this line flattens out, Connor A, if that line flattened out, what would the object be doing?
Slowing down.
If it flattened out, what would the object be doing? Would it be moving at all? It would be at rest. So this upper line, you're approaching zero. You're approaching being at rest. Now, if an object is going to change direction, what do you know about the sign of the velocity? If you're going to change direction, what does the velocity have to do in terms of sign?
Change.
Has to change sign. Has to go from positive to negative, negative to positive. So, let me ask you this. If you drew a position time graph that looked like this, would that show an object changing direction?
Yeah.
Yes,
Why?
because it starts out on one side and then goes to the other.
Does it meet the 3 criteria?
Yes.
How so?
It's stopping at the top.
Is it slowing down before that?
Yeah.
How do you know?
Because it levels out.
Lines become more shallow. Now, I'm going to have a brief delve into calculus. If you haven't had calculus, do not worry about what I'm about to tell you. I'm not going to expect you to know this, but here's how this plays out. For those of you that have had calculus, if you have a velocity time graph, if you take the integral of a function, what are you finding? Who's your calculus? You're finding the area underneath the curve. Okay? So if you evaluate a horizontal line in between 0 and 2 seconds on a horizontal line, you do the integral, you would find the area underneath that. Okay? That's calculus. Don't worry about it. Okay? I'm just telling you. For those of you that have had calculus, there's a simple application of it. Okay? For those of you that had calculus, if you take the derivative of it, okay, that allows you to find the slopes of tangent lines at particular points. Okay? Now, here's the story. Y'all took geometry. If I ask you to draw a tangent line to a circle, how many points does the tangent line touch the circle? One. Okay, so you could have a tangent line like this, tangent line like this. Okay? If you have a curved line on a position time graph, you can draw tangent lines. And those tangent lines gives you what we call instantaneous velocity, which is the derivative of the function if you're a math nerd. Okay? So here's my point. If you look at these tangent lines, what happens to the slopes of those tangent lines? They become more shallow to indicate the object is slowing down. Ah, you're up at the top. What's the slope of that tangent line?
0.
That means the object is doing what? It's at rest. It's stopped. It's not moving. After that point, what do you notice about the sign of the slopes of the tangent lines? Those become negative and they get because it is speeding up. Okay? With that. If you were to find the area underneath the position time graph, what would that give you? not miss this question. Just went over it. Connor asked.
Velocity?
It's the bear game, can I help?
Bo.
Whoa. No, that's not right. Meter seconds, nothing.
That's right. It has no meaning. Okay? It has no meaning. The only time the area has meaning is if it is a velocity time graph. True or false? True or false? If an object stops, it changes direction.
They don't have to.
False.
Oh, is it true or false? If an object stops, it changes direction. False. Give me an example.
I can walk in a straight line, stop.
Yeah, you walk in a straight line, you stop, you keep going, right? So just because you stop, does that mean that you change direction?
No.
No, but can you change direction without stopping?
No.
No, okay, it's a riddle, okay? So if you were to draw a position time graph, here's a position time graph. And you had something like this. Did the object ever change direction?
No,
Why not?
because it kept on going the same way.
How do you know?
Because it never went down.
The slope number.
Yeah, position keeps increasing, the slope is always positive, there's any number of ways you can talk about this. It might have kind of stopped briefly, there might have been a little bit of a section where it stopped, but it never changed direction because the slope never changed sign. Okay, got that? Good, fantastic. Now, we are going to have, and I emphasize the word, an informal quiz. This is not for a grade, okay? This is not for a grade, but it's like a lab practical. So what I'm going to do is, we're going to go back here. Hold on. Just don't leave us. Put it in the camera for now. Watch that. Come here. So, I've got this fan cart. It has a fan, oddly enough, in its cart, that's why we call it a fan cart. Not the most creative name in the world, but you get the idea. So, what I'm going to do is I'm going to take it back there, I'm going to put it on the ground. I'm going to turn it on, I'm going to let it get up to full speed. Okay, so I'm going to have the fan going as fast as it's going to go. So I'm going to do this, get it up to full speed, and then I'm going to let go of it. Okay? And then what I want you to do is observe the motion of the fan cart. And then I want you to sketch a position time graph and a velocity time graph based upon that motion. Okay? This is informal. This is not for grade. Completely informal. Now, I'm going to go back there. I'm going to let this thing go. I'm going to have Abigail stop the fan cart. Do not include Abigail stopping the fan cart. This is not part of the story. Okay? So I'm going to go back there, put it on the floor, it's going to go. Couple of criteria. First off, do you want the reference point where I let go of it or where it gets stopped? Where do you want the reference point to be?
Where do you like it?
Where I let go. It's wise choice. Okay? We could put where it stops as the reference point, but that's just going to get a little awkward. Do you want the positions as they go away from me to be positive numbers or negative numbers?
Positive.
Okay, cool. You could have made it negative, but you decided positive. I applaud you for that decision. Okay? So, I'm going to get the fan up to full speed. I'm going to turn it on. I'm going to let go of it. You're going to see what's going to happen. The other assumption is that the cart never reaches what we call terminal velocity. Okay? Yes, eventually if I let the cart go long enough, it will reach like a maximum speed. It did not reach that point over this short of distance. Okay? So, it did not reach terminal velocity. The fan is going at full speed. I want a position time graph and a velocity time graph. Okay, so if you could kind of turn that around and get it to where we can see what's going on the floor. Okay. Oh, I'm old. You can actually unplug it
Okay.
briefly.
It's a position and velocity.
Position time and velocity time. Okay? Okay. So the fan's up to full speed. I'm going to let go of it. And then we stop. So this was the reference point. There were positive positions going away. I want the position, thank you. I want the position time and the velocity time. And when you get them drawn, I want you, if I need volunteers to come up here and draw what you think the position time graph is going to look like and what the velocity time graph is going to look like. And if you have something different than what somebody else has drawn, draw that. But you only get to draw one line. So when you get it drawn, and again, this is not for a grade. I won't yell at you or beat you with a stick if it's wrong. So draw them up there.
Who's on up there?
Whoever wants to.
Oh, you
What do y'all gotta do?
Yeah, no, I didn't.
Dr. Box?
How you doing?
It's fine. I started drawing a straight line to begin with positions.
Doing a little position time, velocity time graphs. Position time and velocity time. Come on, Luke.
Wait, which one's the
What?
positive?
Go, John.
Huh?
Volunteering.
Positive or camp's the reference point?
I'm the reference point.
Just assume it's going.
And there are positive positions going away from me.
Yeah.
All right.
Are you volunteering?
Yes, I'm volunteering you.
Wait, you want to put numbers on this too?
No. It's just a sketch.
Oh, okay. 'Cause y'all was talking.
You don't know any numbers. You don't know time. You don't know distances. So it's just a sketch. You only have to do one, Luke.
Only have to do one?
You only have to do one.
I don't know, it's kind of hard to explain.
Okay, is that the velocity time?
Yeah.
Okay, all right.
That's a B.
Okay, cool. If you have something different, draw something different.
Go up there then. Go up there. Change it if I know it's wrong.
Yeah.
Do it. Do it. Do it.
I don't know.
I'm lost.
Okay?
Peer pressure.
So we got a velocity time graph one. Huh? Oh, yeah, you guys yourself. Jump up there.
So the snow, so cart moves and then stops.
You do not include the stop. Okay. We got a position time graph. Does anybody have anything else? If I walked around this room, I would see 27 identical graphs just like that. Dr. Botts, are you verifying this?
I might see a little variation.
Little variation? Dr. Botts was a math teacher in a previous life. I've known Dr. Botts since he was 8 years old. Charles, that's Charles. You got anything different?
Yes,
Charles.
Come on, Chuck, get up there.
Charles, do it.
I'm gonna go up there and do this.
Charles got it. Come on, Charles.
Do it, Charles.
Epic line.
Yeah, that's Chuck right
Yeah.
there. Oh yeah, Chuck.
That's Chuck.
That's
I
Chuck.
just want to get the answer, bro. I do. I know. I got it. I got it.
And that's going to be the class motto. That's Chuck.
That's tough.
Okay. Got this. Ooh. Huh?
Okay, yeah. So that's okay.
He's so.
Yeah, I don't know about that, Chuck.
I like that answer.
That's what I have now. That's what I have now.
Is that straight?
I don't know about that,
The
Charles.
second one is supposed to be straight and flat. It's supposed to fit in
Whoa,
angle.
whoa, 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 whoa. I will tell you this, there's 4 lines drawn up there.
Yeah?
One of them is right,
No, it's definitely not mine.
and it is not yours.
It's definitely not mine.
Okay. It's not yours. Now, think this through. Before you draw any graphs, what did you see the cart do?
That's sped up.
Did it start at 0?
Yes.
Yes.
Yes, so right away, Charles, your graph can't be right. Because you have it already moving. But there's aspects of your graph that are right. Just started at the wrong place. Okay. Did it speed up?
Yes.
Yeah.
So right away, if you look at that position time graph that has that straight sloping line, why is that straight sloping line on that position time graph counterintuitive to what you observed? What does a straight sloping line on a position time graph indicate, Andrew?
It doesn't show that it's speeding up over time.
What does it show that it's doing?
It shows that it's moving at a constant rate.
So if I saw that straight sloping line on a position time graph, I would think that cart was just going like this the entire time. Okay? Now, Miss Delzer, you drew a curved line coming up like this. Why?
Because it sped up, so I made the thing steeper as it went up.
The things.
Slope.
Love the English language.
Slope.
The things. Okay? How about you?
I just lost it, I lost it.
It's okay, it happens. So, that's the one line that's right. The curved line on the position time graph is the one line that's right.
I know what I did wrong.
What did you do wrong, Mr. Etheridge?
So the velocity starts, but I said that the velocity like increases.
You did, it does increase. You drew it as increasing.
Yeah, I know, but it's supposed to, it needs to be like, doesn't it? Maybe I don't know what I did wrong. I know I'm wrong.
Does it need to be a straight line?
Whoa, stop the bus. Stop the bus. What does, go back to the beginnings, and the answer actually hinges on that big red sign back there. Okay? What does the slope of a velocity time graph give you? Acceleration. Now, force equals mass times acceleration. Mass is a scalar quantity, which means what? Could it be a negative value?
No.
No, mass is just a number. Okay, 5 kilograms, whatever it is. Did the mass of the cart change as it rolled?
No.
No, we didn't drop an elephant on it halfway through. Okay, mass was constant. Mass was constant. What was providing the force to make the cart move?
That fan.
The fan. Was the fan spinning at a constant rate and providing a constant force the entire time?
Yes.
That's why I told you, that's why I told you I waited until the fan got up to speed before I let go of it. So if the mass is constant and the force is constant, what has to happen to the acceleration? The acceleration has to be constant, which means go draw the line that it should be.
You feeling good about yourself?
Yeah, I actually know it now.
Don't be wrong.
It increases a lot when you know the answer.
Nice. Now, I blame Nike for your wrong answers.
What?
I blame Nike. This is Nike's fault. What's the symbol for Nike? The swoosh, right? You all go, oh, the cart's going faster. I need to draw a swoosh. Okay? Because it's not the Nike stick, right? It's the Nike swoosh. Now, give that a spin. So here's the story. Listen to me very carefully. Acceleration is not how fast you go. Acceleration is the rate at which your velocity changes, okay? It's not how fast you go. You can have a low acceleration and go faster than the speed of sound. It's going to take you a while to get there. So that's what happens with rockets, okay? Rockets don't have big accelerations. They have relatively low accelerations. But if you accelerate for a long time, you can break the sound barrier. So if you look at this velocity time graph, you go back to the beginnings, and you go, oh, what does the slope of a velocity time graph give you? Oh, right, acceleration. F equals ma. So if you want to change the acceleration, if you like the Nike swoosh, if you say that if you draw this line, which I'm guessing some of you did, because you want to believe the purple line. In your heart of hearts, you want to believe the purple line, okay? Because you're going, oh, it's going faster. And the line should slope up because it's going faster because of the Nike influence, right? Line, boring, boring, boring. But this is what's happening. Because if you have this line, you're saying the acceleration is getting bigger. The only way the acceleration could get bigger is if the force got
Bigger.
Did the force get bigger?
No.
Therefore, it should just do what? This line right here. Okay? That's it. That's all it does. Do not make this complicated. It's just going to be that line. Now, if you were to find the area underneath that velocity time graph, what would that physically represent?
Acceleration.
No, the area.
Meters.
In meters, which would mean what in terms of what I just did?
Distance traveled.
The distance traveled. That would be the distance between me and when Abigail stopped it. That's what that would represent. Okay? Now, let's just make the math easy. And let's say that's 3 meters, and let's say that took 3 seconds. Could I, Tyler, could I say, oh, I know how far I went, 3 meters, 3 seconds. Could I take 3 meters and divide that by 3 seconds and go, the car went 1 meter per second? Could I do that?
If you have a constant acceleration.
Constant, but wrong. Don't use the word acceleration.
You have a constant velocity.
Ah, did I have a constant velocity?
Yes.
No, I didn't have a constant velocity. What was I doing? Speeding up. I was accelerating. I can't take 3 meters and divide that by 3 seconds. I'm going 1 meter per second. Because what was I doing? Speeding up. Okay? What's the only time you can do this? When you have,
Constant velocity.
did I have constant velocity?
No.
Therefore, I can't do this. But I can find the area underneath that rectangle. Now, Ms. Delson, this line is right. Why is this line right? Because what are the tangent lines doing? They're getting steeper. Therefore, you are going faster. Okay? Go with that. All right, now we're going to do this again. So, film this again. Okay, now we're going to do this again, but I'm going to give it a push. Listen to me. Do not include the push. We're going to start this analysis from the second that it leaves my hand. Got it? No, we're good.
Okay.
I got you. Got a little excited for a second.
I can tell. I didn't get anything. I was teaching the class. Okay, so here's the story. Again, I'm going to have the fan up to full speed. You're going to start the analysis from the second that it leaves my hand until right before it gets back to me. Do not include the push. Because positive position's going away from me just like before. Okay? So, fan's going to be at full speed. So I'm going to give this a push. Okay? So, ready to watch? Here we go. Boom. To that point. So from the second that I let go of it, right like that, until it gets back to my hand. But do not include me pushing it. Do not include me stopping it. Okay? Again, I want the position time graphs and I want the velocity time graphs. If you drew one of these, you don't get to draw another one. Somebody else has to.
Huh? You just don't need to be wrong.
No, thanks. Because I guarantee you, I know you learn more from what you did wrong than what you do right.
I understand your point.
Me too, but.
So there's the position time graph. There's the velocity time graph. And there's 0 meters per second. Okay? So I want the velocity time
I was thinking.
and the position time. Going? Yeah, go, do it.
I'll take a bite.
Okay.
They got it. They got that.
Guaranteed?
No.
Come on, man.
Typically, Carly.
That is a guarantee.
That's what I'm thinking. It's not a bloody simulation.
You're him. You're him.
Like you're getting it right, you understand.
My velocity.
So I'm kind of like it starts
Does anybody have anything else?
because the velocity starts at 0. Like it goes below 0.
Are you starting at like?
I was gonna have something. No, I started thinking and realized, oh wait. Oh wait.
Everybody has those exact graphs.
Yes.
Seriously.
Yeah.
We're debating it.
Close enough. I used to have a different philosophy graphic when I started speaking.
Well, yeah, no, I kind of have a.
Andrew,
Yes.
is that what you have?
No.
What do you have?
I have the velocity as a curve going away from you and then coming back.
Well, like this much.
Don't throw it up on the board. As soon as it left my hand, it did not start at 0.
Wait, was that all right?
Yeah, there is.
I didn't write it
You're
there.
so stupid, why would you think
So what game right about?
That's where it started.
Because I can't draw.
Okay. I'm glad you talked yourself out of anything, because the velocity time graph is right. Okay? Boring, but it's right. Why is the velocity time graph right?
Because it doesn't. Yeah.
It was moving when it left my hand with positive velocity. As it went away from me, what did it do? Slow down. So did that match the quintessential 3 things that had to happen for an object to change direction?
Yes.
Yes.
As it went away, what did it do? Slow down. It stopped, then it sped back up. Did the acceleration remain uniform?
No.
Yes.
Yes. Why did the acceleration remain uniform?
Because we didn't change the force. and we
You didn't change the
mass.
force and you didn't change the mass. So if the force remains constant, the mass remains constant, the acceleration remains constant. Okay? Good with that. Now, the position time graphs need tweaking. Just a little bit of a tweak. 90% of that position time graph is right. The bottom 10% needs work.
I got
Why?
you. No, that's not at you.
What? Well, let's unlock it, okay?
I guess we're gonna have to straighten out the graph.
Okay.
Yeah.
Because here's the story. What, it's a technicality, but it's important. What is this, if you have this going on at the beginning, what is that showing at the beginning? It's speeding up. Did it actually speed up at the beginning? And I said, don't include the push.
No.
No. So what should this, like I said, from here on up, it's fine.
Should be straight up.
It should be a straight line.
Well, not straight.
It should be like more parabolic, like this,
Straight line, but.
okay? That's what it should be. Why should it be like that?
Because it's slowing down
When did it have its highest positive velocity?
when it left your hand.
As soon as it left my hand, right? As soon as it left my hand, because as soon as it left my hand, what did it start to do?
Slow down.
Slow down. When it reaches this point, what's the velocity?
No.
0. Because the tangent line has a slope of? Then Deacon, after that point, what does it begin to do? With a, what's positive or negative velocity? Do not make this difficult. Rhymes with negative. Negative. Okay. Now, there's a story. Does this line show it speeding up, or does this line show it slowing down, stopping, and speeding back up?
Yes.
Yes. Because what's the sign of the velocity above that line? Positive velocity. What's the sign of my acceleration? Negative. What's it going to do?
It just flip.
No, just from here. Speed up or slow down. Slow down. At that point right there, what's the value of the velocity?
0.
What did it do?
Stop.
After that point, what's it going to do? Because now I have negative acceleration and you're going to